All right, so let's get started. So welcome back, everyone. Okay, so the streaming and the frequent items homework was due today. Hopefully you all finished that. So I've changed the schedule so small amount. So I've just today I decided to kind of switch around the couple lectures that are happening. So right now on regression, I think I'm going to try and cover like all the stuff associated with like Lasso and orthogonal matching pursuit and so compressed sensing today. If we go too fast, I had this kind of split over two lectures. If we're going too slowly, or you think I went too fast, we can review some of it next week, Monday, as well. The goal is I want to talk about cross-validation as something on p-values and related stuff, something I talked about later in the semester, but I wanted to make sure I did this early because I want to ask you use this on the next homework assignment. Even though the regression homework assignment won't be due for like a month, I was hoping to post it before break, right? And so I should cover the material you need to do it before I post it. So I moved some stuff around. So the numbering on the notes, if you click on these things, it's like L19, even though it's lecture 14, which is really 13 because we missed a day. But hopefully, because the links are in the right place, it's not too confusing. So and then, the midterm test is going to be in a week. Feel free. Maybe there'll be time in the lecture on Monday where you can ask some questions about, there might be some space there where we can ask some question about some topic that you want me to go over for a few minutes then. The intermediate report also will be due soon after break, so don't lose sight of that. I have it due on a Wednesday, but don't delay it too much after break because you'll have a bunch of stuff probably dumped on you in all your classes then. And you'll have one-on-one meetings scheduled with me probably sometime this week, and we'll discuss that as it gets closer. Okay. So let's see about that. Here we go. Okay. So what we talked about last time is now the input to a problem is going to be a set X in N. So this is going to be a matrix in N times D. Let's write it. And you also have some sort of signal, which is in Rn. So that you're trying to predict. Basically, what you want to have is that for every data point, which will be an xi, yi in. So xi is going to be a vector in Rd. I want to have a function that goes from xi, and it's going to be approximately equal to the value of yi. Okay, so I want to find a function. In case regression, we'll just talk about these linear functions because you can apply these polynomial and other tricks to kind of extend it to all these nonlinear functions. So we'll talk about this linear function. That means that this model M alpha is actually, it's sufficient to think of this as actually being xi, a dot product with this alpha vector, and I want this to be equal to yi. Okay, so this is what we talked about. And so a good thing to think is that the goal of this is actually to predict the value of m of xi where x is new and given, and y is not, right? So let's say I'm given a new observation, which is, some point. So for x in RD, I'm given a new so let's say one of the data points has a simple example would be that it's the D, let's say D is 20, the 20 previous kind of closing prices of a certain stock, and I want to predict what the price will be at the closing of the 21st day, right? So then y, y would be what the value is going to be on the 21st day. Can I predict this from the last 20 days? And I want to model that kind of based on historical data tries to predict this. So I'm given the last 20 days of a stock price. I want to predict what the value is going to be on the y day, and I don't know what that's going to be. So I'm trying to predict for a new value x what the y value is going to be. Ultimately, this is what my goal is going to be, and I'm going to try and learn from the data something where I do have the x's and the y's so that I nearly match this. All right, so this was, remember, this is the basics of what the model is. Okay, and so one thing we talked about last time, the way we're trying to predict what this is, we had this L1S, so objective function, where we took in a data set X and Y, and some model, and we want to evaluate this model. And basically what we look at is the sum over all xi in this data set, the xi, so the model minus what you actually observe. And this was a 2-norm. This is the least squares cost, right? So I make a prediction. How far is that from the actual model? This is not a norm here. These are just values. So if I can write this as a matrix product, this is equivalent to x alpha minus this whole y vector, right? And then I'd write this as a matrix product. And then with the lasso, I'm adding on a term here, s times alpha 1. So I put a penalty if the norm of my model, if the model has large coordinates, as large coefficients, I want to penalize such models. So I want to minimize this overall cost function. And so I'm adding on this term which says, okay, not only do I just care about how close am I to the prediction, but I want to bias towards these smaller coefficients. Okay, and so as I mentioned in the previous lecture on Monday, that this if you choose S correctly, you can actually have a new data. When you draw a new data from essentially the same distribution here, there is a value of S, which will give you a better expected error, but it will add some bias into it. Okay? And I mentioned that if I put a 2-norm squared here, then there's a nice closed form solution for this. But with the 1-norm squared, there's not a nice closed form solution, but that it will induce sparsity. I'll tend to have I want these values to be small, and in fact, a lot of them will be so small they'll actually be 0, right? Where if I put the ridge regression with the L2 norm here, I'm not getting this sparsity effect. And okay, so the two things I kind of want to do, main things in this lecture, is kind of show you some ways how to compute an alpha that tries to minimize this objective function, which is a little trickier than without this term or with a squared L2 norm squared constraint. And also kind of explain why it's inducing sparsity. Okay, so it'll be a nice geometric intuition that I'll go through that'll explain why this is inducing sparsity. Okay, and then I also hope to talk about this idea called compressed sensing, and we'll go through kind of a very basic version of this, where if you're given data drawn in some way with noise, but you know the solution is sparse, you can actually recover the exact answer, even though you're given the data with noise. Okay, so you're given noisy observations, but you know that the model is sparse, then you can actually sometimes recover the exact model, even though there was noise in the process of sensing. And it's kind of a cool application of these lasso approaches. Okay, and kind of a cool thing that you can do in its own right. So hopefully we get to that. If not, we'll push it into the next lecture. Okay. So if I take this lasso objective, I want to think about and I'm giving you this. Okay. So how to find alpha, right? I no longer has this least squares thing where I can essentially take the first derivative and then solve for what alpha is. I can no longer do that because of this constraint, which makes it not smooth. So it may not. There may not be there's not a simple closed form solution for this. And I'm going to give you a hint that alpha is going to be sparse. Okay, so the larger the value of S is, the sparser alpha will be, and we'll see why this is. But kind of the hint towards solving this is that alpha is going to be sparse, which means that most alpha I are going to be exactly 0. Okay, so that's going to be the hint towards solving this. All right, so we're going to start with something that is not is not going to actually have a guarantee that it's always going to find the right solution. If there's a small enough amount of noise, you can end up, and things are sparse enough, it turns out that you can say that in some cases this does find the exact right solution, but it's going to work pretty well in practice, and it'll be a pretty simple way of approaching it. The same way with k-means clustering, we don't have like a great exact solution for that, but there's a common algorithm that we run anyways. Right? Okay, so how would we go about trying to find these alpha coordinates? Remember that alpha equals alpha 1, alpha 2, up to alpha d, right? So it's this d coordinates, and I say many of these are going to be 0, and I've got this cost function. Let me just think a little bit before I tell you something. What would you try and do? Yep.
Maybe like compute the cost function with some of the parameters set to 0 and see like which one gives you the best cost function.
Yeah. So so what the suggestion was to set a bunch of the parameters to 0, which is actually the right thing to do, and then check these different combinations and see which one does the best, right? So maybe even ignore this and then set stuff to 0, and then this I know I can solve in a closed form, right? If I ignore this part, and maybe setting stuff to 0 was a good way of kind of taking care of what was supposed to be going on here. Okay, so this is, in some ways, is the right solution, but it's also the way you described it not quite right, because if I want to choose, say, all sets of size, let's say I think 10% of the coordinates are non-zero. So it's pretty sparse. 90% of them are 0. If there are 100, that means 10 are non-zero, and 90 are 0, right? So that's a pretty sparse model. that's a lot of combinations I need to check. I need to do like 100 choose 10 combinations, which is going to be too many. Okay, so what people often want to do is put an L0 constraint here, and that just says I just want to count the number of them which are non-zero, right? And fix that number, which is essentially what you want to say. And this problem is kind of computationally hard. It's known to be computationally hard to put an L0 constraint here. An L1 constraint, turns out it's easier because this is still going to be a convex function here. And we'll get to this a little bit. But what you did say was right, is I want to set kind of a number of them to 0. And kind of what I do is I want to set all of them to 0 except for 1. At this level, there aren't that many combinations, right? So I want to try, and instead of thinking of setting them all to 0 except for 1, I want to try setting each one as non-zero. I want to say, find the single coordinate which tells me the most about this. Okay? Tells me the most about the objective function. And then maybe I set that value, and then I take that part out from what I found, and then I'm gonna repeat this. Then I'll say that one's now set. Now I find the next coordinate which does the best job. Okay, so it's this greedy approach. All right, okay, so what we want to do is we're going to have this greedy solving for these alpha j, and so kind of greedily solving for them is not what this is typically called in the literature. This idea is called orthogonal. So matching, so pursuit, or OMP. The pursuit is kind of the term that corresponds with greedy. The orthogonal matching part is a little bit harder to explain. After I describe it, maybe I can try and give intuition of where that's coming from. This is sometimes also called forward. So subset, so selection. The idea being I'm trying to find a proper subset of the right coordinates. Think of like feature selection. It's often associated with feature selection in some ways, where there's a set of features or coordinates that might be useful. I want to find the most useful ones. And the forward means I'm adding one at a time greedily forward. There's backward subset selection where I'm trying to set them 0 one at a time. Which one setting to 0 will affect things the least? Okay. So how this is going to work? Let me try and write down and kind of step through driving algorithms step by step, and then on the next slide I'll actually probably write it in a way that looks a little prettier. Okay, so I'm going to start by, so I'm going to basically all of my signal. My signal is y, and I'm going to set this equal to r. Okay, so this r is going to stand for the residual. So I start with all the signal y, which is what I'm trying to predict from my data, and then I'm going to have this. I'm going to pick one coordinate, and that's going to account for some of y, and then I'm going to subtract it off, and the rest is going to be the residual of the signal. But initially, all the signal is in the residual because I haven't picked any coordinates, right? And I haven't picked any coordinates because I've set alpha equal to 0. All the alphas are 0. Okay. Okay, and then I'm going to go through a for loop. Let's do this from j equals 1 to t, and t is kind of be the number of coordinates I pick. Okay, so I'll stop when I pick t of these coordinates. Let's call this k. Okay, this t is going to come up in other ways. Okay, so I'm going to pick one coordinate at a time, and I'm going to do a for loop over this. Okay, so the first thing I want to do is I want to identify the coordinate which is going to tell me the most about my about my objective function. Okay, and which one, how do I know which coordinate tells me the most about my objective function? If we remember, we have a cost function up here, which is basically x alpha minus y 2 norms squared. And then there's this, right, so plus some regularizer. So which one can tell me the most about this? So it turns out if I take this least squares and I do an expansion of it, this is going to be minimized when I'm going to maximize a cross term, right? So there's going to be this okay, so I'm going to take the dot product R with xj, and so if I look at my model up here again, I've got this y, which is supposed to be equal to x times alpha. Okay, so I've got this model where y is supposed to equal to x times alpha, y is equal to r here. So I want to find the y which is most, every element of alpha here corresponds with a column of x. Okay, so this will be column xj prime. Okay, so, and it's going to be interesting. I'm going to be able to find, if I make the associated column alpha j here, if I make this large, it will align well with y and capture its norm if this dot product is large. Okay, so I want to find the column xj which maximizes this dot product. So I'll say an R max kind of j prime in the set of these columns, which this quantity, the absolute value of this quantity is going to be large. And I'm going to set this equal to j. Maybe that's why I do an I here. Okay, so this can be, let's call this j star or ji. It's the coordinate I pick on the ith step. Okay, so this will be my choice of which coordinate is going to be the most interesting. Basically, if it's correlated with the residual. All right, so if you guys remember what these kind of, there's a way to think about these vectors of, so if this is x1, x2, x3, x4, say x5. So if these are the columns of x, okay, so remember the data points are rows, right? But columns are kind of, I can think of these columns. And so these columns are going to be correlated with the signal y if the dot product is large, right? So now if I drew the signal y here as another vector, right? These are all in, this is all in the space Rn. Sorry. Okay, so this is in the space Rn. Each column is a length n column, and so these are, can think of them as vectors in Rn. And I basically want to find the column, in this case it's x1 here, which has the largest dot product with y. Right, so think they're scattered all over in this big n-dimensional space, and the dot product means that they're correlated, they're kind of pointed in the same direction. So if I try and approximate y with a single column, then what's left over will just be this residual vector here. Right, so I'm going to have some leftover error. I pick a good color. So if I project, onto here, and I project onto this, this green vector will be the leftover after I make a prediction with x1. right? I can actually represent this point, not y, but I can represent this point in the span of x1 by just scaling x1 by, like, if this is the length, then by like 1.1. X1 gives me a point here, and that's pretty close to what I'm trying to predict with y. So I try and find the one that does the best job predicting, and then r is what's left over here. Right, so I want to subtract off r, and now I've got a new vector, say r, that looks like this, which is just translated down here, and then I try and find the next vector, which is going to help me predict what's going on with r. Right, and I just repeat this process. Okay? Okay, so let's try and write this algorithm out in more detail. So after I found this value, this column, which is the best, I need to then set alpha ji star, right? Okay, whatever. The coordinate that I picked, I need to solve for this alpha here, and this is going to be arg min of some gamma of r minus xji star of gamma squared, and maybe I add this residual term as well. Okay, so if I can optionally add here, and this will help induce sparsity as well. Okay, so I can solve for this that minimizes this cost function here. Okay, so I said I didn't know how to solve for this minimum of this cost function, so why do I think I can solve for it now? Well, now it's only over a single scalar value. I'm not solving the vector valued version of it, which I said was difficult to do. I can solve for just a single scalar value, right? And this I can do. I can take the first derivative of this expression, and then I can and then I can also take the first derivative with this. Now this one has a kink in it because that, but it's okay. There are two parts I need to check for. It's on kind of greater than 0 or if it's less than 0, and I can find the minimum. So this I can solve for now because it's a one-dimensional problem. Okay, so I can solve for the best prediction here. Maybe it's not exactly the prediction, the closest point, but maybe it's shrunk by a small amount. It's probably what happens. Okay, and then I'm going to update and set the new r equal to r minus xji star of alpha ji star, whichever I solve for, right? So I took this guy and I took the column. I figured the value I solve for here. I subtract that from the old residual and I get the new residual, and then I go back to the start of the for loop. Okay, and then at the end I return alpha. Right, so every time I do this, I've set one coordinate of alpha, and I've explained part of this residual vector, and it should keep getting smaller. Okay? So this is the algorithm. It's a pretty simple greedy algorithm. So you do it. There's some a little vector algebra you have to do. You have to take, so you check over all values of j here. You take their dot product with r. You take the absolute value. That's the selection. For this, you need to kind of like. I don't have it in front of me, but this is not a hard thing to solve for the two cases, which could be the minimum of this. And so I can solve for this, and then I take it, multiply by this vector by a scalar, and I subtract, and I just repeat. Right? So it's a pretty simple algorithm. Okay, and this is orthogonal matching pursuit or Ford subset selection. Okay. And so the orthogonal matching pursuit comes from the residual vector is always going to be orthogonal to the subspace that you've found so far. So that's, I'm pretty sure that's where the name comes from. The matching part, I'm not, I guess, maybe this is what's called matching. I don't totally know. But so, okay, so this is a procedure which will help you solve this Lasso formulation. Okay, I think in case, as a backup, in case my handwriting not too bad, I've written it Up here again, I think this is basically the same thing. Okay. Okay, and so this is the same algorithm. Any questions about how this roughly works? Pretty simple. Okay, so and we'll see. I'll talk a little bit about when this can find the exact right solution, and then I'll mention another algorithm that is guaranteed to find the exact right solution, but is more complicated, and the runtime might in some cases get very large. Okay, so what? So the next thing I want to do is explain why, if I do find the true minimum of this cost function, all right, so let's write this cost function up again. X alpha minus y right? If I do find the true minimum of this cost function with S large, then this is going to induce sparsity. Okay, and I said that there's this equivalent formulation, which is just to minimize this L2 problem, but have a such that so one here that that the one norm is less than t, right? So that instead of, I can say, I want to solve the exact L2 formulation here, right? The least squares formulation, but put a hard restriction that the one norm of the coordinates is less than some value t, right? And so as S gets larger, then t gets smaller. Right, so I said that there's this trade-off that as S goes up, then T is going down, and so vice versa. As S goes larger, I get more sparsity. So that means as T gets smaller, I restrict that the L1 norm of alpha is smaller. That means that more things have to get close to 0, and in fact, I'll get more actual zeros going on here as well, right? Okay, so I want to try and explain why this is the case, and also why the ridge regression version, where I put a 2 norm here instead, does not induce sparsity. Okay, and the right way to think about this now is to draw a picture. And again, hopefully my drawing goes well. I've got a backup picture on the next slide. Okay, so I want to think about the space. This is going to be RD, and this is going to be the space of alpha. Okay, so think of this as alpha 1. This is the alpha 2 coordinate. And then there's also going to be alpha 3 coordinate and so forth. There's a d-dimensional space here. Okay? And so now I want to say, and now like in this space, somewhere in this space is going to be, let's say let's make it right here. We'll call this alpha star. This is going to be arg min alpha of x alpha minus y. Okay, so this is the least squared solution. Somewhere in this space is the least squared solution here, right? So it's, in this case, it's a positive alpha 1 coordinate, a positive alpha 2 coordinate. Maybe alpha 3 is negative, something. This is the least squared solution. Okay, and so now what's useful to do is to draw this restriction, right? Remember, I restricted the alpha 1 had to be less than t. So if you remember what the L1 ball looked like, so if this was the value t here, then the L1 ball looks like this. Kind of looks like this. In the 3 coordinate, it kind of comes out. It's this kind of this rhombus diamond sort of shape thing. Okay. Whereas, so this is inside of here. This is going to be alpha 1, 1 less than or equal to t. That's this region inside of this diamondy shape here. Okay. In contrast, I want to draw another shape here, which is, right, so this is going to be alpha 2 is less than or equal to t. Right, so I can put the similar sort of constraint on sort of ridge regression, and that gives me this L2 ball. Right, this is the rounder sort of shape here. Okay, and so now I want to find the min cost solution, which neither of these are, if I set t to be such, if I make t large enough, then eventually the alpha star will be inside the ball, right? And then I can return the alpha star, the least squared solution. But if t is smaller, then I can't return that solution. I need to shrink it somehow. Okay, and so what is the? So I can choose any point in here, and it's basically going to be somehow the closest point to alpha star. It's not L2 closest. It depends on some. It's going to turn out it's going to be so a Mahalanobis distance from a star. And that's going to depend on essentially the the singular vectors of x in some way. And let's not exactly worry what that looks like, but I'll draw a picture. Okay, so I'll draw a picture here that there's going to be some cost function where, the zero or the minimum cost is at alpha star, and then as I go out, it's going to have these elliptical shapes. Everything on the same ellipse has the same cost, the same L1 cost. It's going to be something elliptical in this way. Okay, and so now I should have drawn it the other way. Well, it's still going to work. Okay, so if I draw this very carefully, okay, so this will end up being the solution for alpha 2 star, right? So this will be the minimum cost solution that is going to satisfy this L2 constraint. And if I make it, I have to, kind of add a small amount of cost. Let's see if I can draw it here. Okay, so now the minimum cost here, this is alpha 1 t. Right, so this point right here is going to be the minimum cost solution inside of this L1 constraint ball. Okay. Okay, so this is kind of the picture of what's going on here. Now, and this picture should help illustrate why sparsity is being induced. What is particular about this point here? What's happening here?
It's on the x-axis.
Right, it's on the x-axis, which means the y-coordinate, the alpha 2 coordinate, is 0. Right, where this one is not 0. Right, the L2 does not necessarily induce sparsity. It might accidentally, if these happens at exactly the same spot, which almost happened the way I drew the cost function. But in general, so if that happens, that would actually be a coincidence. Okay, there's no reason the L2 shape, the ridge regression, shrinks all the coordinates, but it should not exactly hit right on the boundary. Okay, but with the L1 cost function, it's pointier. It's this pointy region that's allowed to be in, and it's more pointy along the axes where some of the coordinates are 0. So it's much more likely to hit where it's 0. Let's look at the picture. I had a backup picture here where I oriented the other way. Okay, so this is alpha star with ordinary least squares, right? And so this is the L1 cost solution with Lasso, where it hits exactly on the boundary here, and the L2 cost minimum solution is on this blue shape. Okay, and so if you restrict to this L1 cost function, you get this pointy restriction. And as we mentioned, this version where you have this hard constraint is going to be kind of equivalent for every value of s. There's an equivalent value of t where the problems are equivalent. So that means even with the soft constraint, I'm still biasing towards these sparse solutions with the L1 constraint. Yeah.
So what defines the angle under which you draw the ellipse? Like, is it going to be either perpendicular to the x-axis or under some angle?
Yeah, so it's going to have to do with the it's going to have to do with the singular values of x. Okay, and maybe it has to do with y. I don't remember exactly the derivation offhand here. But so if you have more, like if you have larger coordinates, so the alpha 0, or so the alpha 1 coordinate, say the x-axis here, corresponds with the first column of x. Okay, and so if those column values are actually going to be larger, then by moving a smaller amount along alpha 0, in the alpha 1 direction, I'm going to change the cost function more. Right? So if the values in the x1 coordinate, the first coordinate of x are larger, then that direction is going to be more sensitive. Okay, but I can't just look at the individual coordinates. I should actually do this singular, look at the singular values, which give me a different basis, which controls what the direction of going on here. And we'll talk more about singular values after the break, and then if these notions are not so clear, hopefully where you get ellipses from data like this, we'll see how to derive ellipses from singular values in that case. But it has to do with the singular values. So the same argument works if you just force this to be, if you force it to be a circle instead of an ellipse. Right, so there is some ellipse which controls this. This is more of an intuition of what's going on. I mean, the danger of this is that. So, yeah. So there's one important point here that does come up with this. So I mentioned in the when we had this lecture on the distances, and we talked about these LP distances, about how if I had this road sign, picture of the road sign where they have the date the city was founded, the population, the elevation, and they kind of added these all up, and this is essentially, and so if I'm kind of making coordinates where it's height and weight, and I want to use this to predict kind of the age someone is going to live to. Well, actually, in the basic in the basic least squares formulation, that's actually valid to do. If I just look at the least squares part, that's perfectly reasonable to do, right? I can use height and weight to try and predict someone's how old they're going to live to, right? That's a reasonable thing too. I'm not mixing coordinates. Actually, the coefficients in alpha are essentially canceling these coordinates. Okay, and I'm just learning to predict a model that predicts the age someone lives to. But as soon as I add a regularization term, either an L2 or an L1 regularization term, I'm now saying all these coordinates are essentially equal in some way. Okay, and so the scaling of the ellipse in some ways has to do with the choice of coordinates. If I measured height in inches instead of feet, or in meters, or in centimeters, that's essentially going to change the scale of that particular column in my data matrix X, and that's going to change the shape of this ellipse. And so there's some danger in kind of mixing coordinates when I'm doing this. So often they kind of normalize. You know, if you look at the very principled way of doing this, they say, well, you kind of have to normalize the coordinates first, or you need to have an example like this stock data I used earlier on, where I used the 20 previous days of stock data. Those all have the same units, so there's no issue there. So there is these kind of issues to worry about, and I'll mention these a little bit. Yeah. So that's a good question to bring. All right. So there's not a great answer. Maybe you should normalize kind of the columns before you do any sort of regularization here. Maybe that's the best thing to do. I don't have a but maybe one column is more important than the other, so you don't want to do that, right? So these are somewhat of a modeling choice. So, okay. What did I want to say next? Okay, so, all right, so, but I want to, so I think I'm doing, yeah, so so far I'm covering all the stuff I wanted to cover. So I want to get back to using this picture to give intuition for a different algorithm to solve exactly for this Lasso formulation. But at first I want to talk about this compressed sensing problem. Okay? Okay, so this is kind of this odd formulation which the first time you hear it, it may sound like it's going to be impossible. And I'll set this problem up one way, and then we'll look at it kind of so kind of a different way as well. But basically, it's going to be the case where I'm going to try and solve for y. So I'm given y and I'm given x. And it's going to look like this. Okay, so I'm going to look at a problem here where this is n by d. Okay, and so this is going to be the case where d is going to be larger than n. Okay, so if I remember back to the least squares formulation, right? If I just look at the least squares formulation here, I said that I could say that alpha star under the least squares was going to be x transpose x inverse x transpose y, right? That there is this closed form solution here. And if you've taken like a linear algebra course, you might look at this and start to squint your head and say that now this matrix here is going to be a d by d matrix, right? So it's square, which is why I need to take the inverse, but it cannot possibly be full rank. I need it to be full rank to take the inverse. So this is a problem. I shouldn't be able to solve this. In fact, what it means is that there's actually an infinite number of solutions which should solve this exactly. Right? So this formulation should not even make sense. Right? There's a continuum. I think is it the null space? Not the null space, but the
Free variables.
What the
Free variables they're called.
Yeah, there's a space of free variables which will actually exactly recover y. Okay, this would be like overfitting, right? This was I can choose way more parameters than I have actual data points, right? So this seems like I can't. This doesn't even make sense to do. But it turns out if instead I use the Lasso formulation where I enforce sparsity and I set the norm to be small enough, well then I can actually solve this in a way that makes sense. Okay, so if you use the Lasso formulation and you add an L1 constraint, then this question makes sense again. Basically, I enforce that if I say that if I say Lasso and say that A has less than, let's say, less than n, so non-zeros, right? So I somehow choose my Lasso constraint, the S or the T parameter, so that alpha must have less than n zeros, right? So now I have fewer, if I know what coordinates those are, I have fewer I have fewer unknowns than I have data points, and I can kind of solve it again. The thing is, I'm not saying which ones are going to be non-zero. So I still actually have a much larger free space than is possible, but it turns out you can still essentially solve these questions, and they still make sense. Okay, I may need to make alpha sufficiently less than n for this to work, right? So it must be much, much less than n. Okay. Okay, so this is one way of viewing the setup. I want to kind of look at a different way from compressed sensing, and one way of thinking about this is that, let's say I'm taking a picture with a camera, right? And if you take a picture with your phone, what it has is it's got a lens here, right? And in the lens, behind the lens, it has the sensor, and it has all these, essentially each pixel in an image is going to be an individual sensor. Maybe newfangled cameras are moving maybe in some ways a little bit beyond this, but basically this is how it works. Each pixel in the image has its own sensor if it's stored in RAW, right? But I never store the photos in the RAW format. I usually store it as so it's like a JPEG, right? A JPEG is a compressed representation of what I've picked, and usually on your phone you never preserve the RAW image. There's often hardware actually that automatically converts it into a JPEG before it ever shows up in the software. Okay, so I'm taking all this data, think of that as the d different coordinates here, and then my representation is going to be some compressed n-dimensional thing. I only have so many bits of information that I have. Okay, so if I'm going to get a compressed representation, maybe I can I can do something smarter with how I do the sensing. Okay, maybe I don't need all of those sensors, or I can do something smarter. Okay, and so this is this kind of idea of putting compression into the sensing in some way. I can't make it quite adaptive, but I'm going to kind of, instead of having individual pixels, I'm going to kind of randomly mix the pixels together. Okay, this will kind of sounds weird, but I'll try and kind of write down something that's kind of a mathematical, simpler version of the same problem. So I'm going to think of this sparse sensing framework, and so I've got an example up here. So let me try and annotate this example. So this is going to be an unknown signal. Okay, and so in this example, we're going to enforce that the signal is, I think this is like, is it 16 or 32 bits maybe, and they're either 0 or 1. Okay, so there's kind of, think about it as these are the pixels in the image, and the image is either black or white, and it's black if there's a 1, or it's white if there's a 1, and it's black if there's a 0. Right, so I want to find the white are the light sources, and I want to find these 1, 2, 3, 4, 5, 6, 7, 8, 9 light sources here, and that tells me everything I need to know about the image. Right, in practice, you actually have some other compressed representation, but this is kind of would be a little simpler to in order to look at. Okay, so instead of capturing each individual pixel, I could do 32 individual observations, which is the standard way to do it. I'm going to make these kind of combined observations where I kind of randomly mix everything together. And this is going to be, and this is my, this is going to be my sensing vector. So this will be the ith sensing vector. I'll do this multiple times, but this is one of them. And it's going to be drawn from -1, 0, +1, I think, to the power d. So it's a vector of length d, the same length as the signal, and each entry is randomly a -1, a 0, or a +1. Okay. You can maybe just have -1s or +1s, and then it's actually going to kind of look kind of like the count sketch, and we'll see after the break how these are actually going to be more similar even than that. Okay, so I have this random thing, and so that means that, okay, and so this is kind of a sensing vector. So think of it as like a mask on top of all my pixels. And I'm going to record now a single value yi. This is going to be my my observation, right? And it's going to be a dot product with the signal and the sensing vector. I'm going to get one scalar value here, right? In this case, I added them up. It's going to give me a scalar value of 2. Okay, I get a single scalar value of 2. And so think of it as putting a mask over my pixels. If it's a 0, that means I've blocked it out. If it's a 1, I let through whatever is happening. If it's a -1, I have I'm reversing the signal some way. Okay, not quite sure how that works with the math. There's a way to make this with just 0 1s, and then you have to adjust the values later. Okay. Okay. So and then I add them up, and I get a single value 2, and then I'm going to repeat k times. Okay, so I'm going to repeat this k times. Okay, and so basically I'm going to get x, which is going to be, I think each of this sensing signals, yeah, so this is going to be x1, x2, up to xk. This is x, right? And then this is going to output to give me y, which is going to be y1 up to yk. This is going to be a vector here. And so basically what I'm doing is I'm multiplying this by some signal, which is s. Okay, so this should kind of look like the picture over here, except, you know, now basically s is equal to this alpha unknown model vector that I'm trying to recover. So what's known is that this is going to be known. This is kind of chosen by my sensing algorithm, and this is going to be observed, right? So this is what's observed from the data. This is known. And then I want to try and recover S, that true signal from this. Right? And I claim that if I use some Lasso version, like orthogonal matching pursuit, or one of these, there's a whole kind of series of approaches you can use on here, where orthogonal matching pursuit is the simplest. And if I know that S is going to be sparse, then I can recover S if I make K large enough. Okay, and I think K needs to be something like, so let's say if I have M, this is going to be the number of non-zeros, okay, and D is going to be the length of S, right, so this will be the number of coordinates. Then if I make K equals to be about some constant times M log of D over M, then I should be able to recover this. Right? So K is going to be roughly the number of non-zeros. Right? M, so there's going to be some constant here. Some constant, and this value, this is, depending on the algorithm that you use, between like 4 up to 20. So if I use orthogonal matching pursuit, which is not as good of an algorithm, if I still set C equals to 20, so 20 times the number of non-zeros with a log factor, then I should, and I choose X correctly, then I should be able to recover the exact signal here. There are better algorithms, which are more complex, which we're not going to talk about in this class, unfortunately. But you can get it down to like 4. Okay, so only 4 times the number of non-zeros. And if you think of what this log term is doing here, this is like log of d. Well, I need basically, just to tell me which coefficient. Think of it that like a label of which entry in here. It takes me log d bits to tell me a label of which bit is the non-zero, right? Or if I actually just store the gap between consecutive ones, then it's roughly log d over m bits, right? So this is basically up to the information kind of the information theoretic limit of how much data I actually need in order to recover this. So this is a pretty kind of, from like information theory kind of people, this was kind of discovered only about like 15 years ago that you could do this, and this was kind of like, was like mind-blowing that you could recover the signal from these kind of noisy kind of these combined together these measurements. Okay. How do you choose x? If you need to choose it if you choose it at random, it works pretty well. So you want to choose it at random. Needs to have some property where each of the vectors x are supposed to be roughly orthogonal to each other. And it turns out if you choose them at random, then they're going to roughly be orthogonal. Okay. So there's like these RIP conditions you have to go through. Okay, I'm not going to describe them in full. The full formal definition of that. But if you choose them at random, this basically works. So if you do enough of these, and then you use orthogonal matching pursuit, which we talked about, you can recover the actual signal. So, okay, so I think I've got an example up here. Let me try and, okay, so the orthogonal matching pursuit here is a little bit simpler. This, if I still just choose something with the dot product, right? Whichever dot product is the largest with the actual this residual. This should actually be initially this is going to be s. No wait, this one is still y. There we go. So and s, I'm going to try and learn the coordinates of s. They're going to take the value of the gamma j's, right? So if I set here. This one, if I know it's 0, 1, I can set to, I can basically skip this set and set this to 1. If I choose it with the largest dot product, I set this value to 1, and then I subtract off the residual. This term just becomes a 1 here. Okay, and then that means I'm basically setting this Sj value to 1 if I choose it at some point. So let's go through this. I've got an example set up, and hopefully this works. So let's kind of walk through this, and I think I have it set up so it's too small to work in theory, right? It's not. There's no guarantees that something this small will work. I've got in this case I've got m equals 3 and d equals 8. Right, and the number of actual observations I need to make, k was supposed to be basically like 20 times m times log of 8 over 3, right? It was supposed to be something like this, and I've made 6. Okay, so. Right, so the theory is not backing up. It should work, but I think I've chosen it carefully so it does work. Okay, so just to kind of illustrate kind of how this should work.
Are you using log base 2?
Yeah, I think it's a log base 2. Yeah, I mean it goes into the constant somewhere and these numbers. Yeah, so don't take 20 as being precise. Yeah.
Dimension 9.
Was it 9? 1, 2, 3. Yeah, maybe it's 10.
Oh, 10.
10. Okay, so slightly worse here. Okay, so this should be even harder. Okay, by less than a factor 2 harder, but okay, or less than 1 additive, more observation harder, I should think. Okay, okay, and so I made this observation. I got out this observation y. 0, 0, 0, 1, 1, minus 2. Okay, so with the unknown signal, now let's see if just from x and y, I can actually recover s. See if I can do that. Okay, so the first, basically what I want to do is I want to take the dot product of y with every column of x and see which one is the largest. You guys look at it, and I'll look at my notes and then see if we come up with the same thing. Okay, so okay, so I think I know in my notes what the right answer is. So let's, so if I take the dot product with the first column, for instance, I get 0 plus 0 plus 0 plus 1 minus 1 plus 0, right? So this dot product is 0. So this is not going to be the largest one, okay? It's not correlated at all, in fact. The next one's also going to be 0. This one is going to be minus 1 plus 2. So this is plus 1, right? I'm looking at the absolute value here, so that's a 1. Okay, the next one is going to be plus 2. Okay, so this is a candidate. The next one is going to be plus 1 plus 3. Right? Does that seem right? Okay. And then the next one is going to be 1. And then minus 1 plus 1, so 0, plus 2. This one's going to be 0. Let's see. Minus 3. Okay. And this one's going to be plus 4. Okay, so that one looks like it's going to be the maximum, and this one will be 0. Okay, so column 9 is plus 4. Okay? Actually, if you think about it, because I restrict the signal to 0, 1, any negative number is actually going to be bad, because I can't give a negative coefficient. Okay, so column 9 is going to be the best. Okay, so what I'm going to, next is I'm going to do is I'm going to set the residual after one step to be y minus column 9, so x9. So this is going to be 0 minus 1, so minus 1, 0 minus 0, 0, and then 0, 0. So and then the minus 2, minus 1, minus 2, so that's going to be 1. Okay, so this is a smaller vector. So the norm of, just the L1 norm of y was 4, now it's down to 2. Actually, so I've reduced the norm of y, I've captured some of the information here. That's good. You generally want the norm of your residual to be decreasing, and that's happening here. Okay? So now, so that's the result here. I'm not going to pick this column again, so let's just circle that one. And so now let's go and repeat this process and take the dot product with the other columns. Okay, and so the first column is going to be 0, right? The second column will be minus 1. Okay, the third column is going to be 0. Right? The fourth column will be 0. The fifth column will be, I have a minus 1 and plus 1. These will cancel. This one is 0, 0. This one is going to be 1, and this one is a 0. Okay, so now I have two options, either column 2 or column 8. Right? Column 2, actually, it's a negative value. I know that it's going to be positive, so I'm going to take the 8th value here, x8. Is this what my, okay, I think I'm deviating from my notes, so we'll just, I may have changed the example in my notes, so so let's just see how this goes. Okay, yeah, let's see if, just want to check if I have different notes here. And all right, so let's okay, so let's go with this. Now R2 is going to be equals to R1 minus X8, and this is going to be so I have -1, -0, so I still have a -1. Okay, I've got a +1 here. I've got a -1, a +1, a 0, and a 0. Okay, so my norm didn't go down. Yeah.
Sorry, I'm a little confused on that R1. Is that first element supposed to be 1? Like a positive 1? Because you're taking a 0 minus a -1, and that would have some other kind of right?
Yes, that's right.
Okay.
Yes, so I made a mistake here. Okay, that's fixed. So all these values are wrong. This is good. It's live examples. So okay, so good because this actually didn't do a very good job. My norm went up. So
The last element would be -1 as well, right?
and then this would be, yeah, this is -1. Okay, good. So now I think a lot of these examples are the same, but this becomes a +1. These are still 0, 0, 0, 0, 0. This becomes a -1, and that one's still 0. Okay, so this the big difference is now instead of choosing this column for the same reason. So this is -1. Now I'm going to choose this column instead. Okay, hopefully this makes the example work a little bit better. So x2, good. So what's going to happen now? This term is going to go to 0. I'm going to get a 1, a 1, a 0, 0. I'm still not picking what the correct coordinate is, but that's, well, let's just go with it. And -1, right? So the first coordinate I picked, right, was actually this coordinate here. Right, so I picked x9, which was the correct coordinate. The second one, I should have picked column 3 or column 6, probably, right? Because these were the ones I should have picked. I didn't. I picked x2. I'm deviating from this, and so this is one of the things that can go wrong with orthogonal matching pursuit. So I got to demonstrate this instead. Okay, so let's just do one more step. So there are variants of this where you can like add a correction, where after you've done something, you can go back and revisit it. So if I find another column, let's see if I find the third or the sixth column in the next time around, right? If I take a dot product now with column 6, what's going to happen? Is that going to be good? So let's. So if I take a dot product with column this one's again going to be a 0. We'll skip this one. This one will be a 1 and -1. This is going to be a 2, which is good. All right, this one, the next column is going to be a this will be 1, and I'll skip doing this. Let's see if I pick column 3. What's going to happen is that I will subtract this. Let's say I pick column 3 as R2 minus X3. Right, and so I subtract this off now. So I have a -1. I'm going to have a 1, a 0. This is going to be a 1, a 0, and a 0 now. Okay, so this is not reduced the norm, but probably now if I go back and I examine the effect of column 2, it'll make sense to subtract off column 2 again, and then it's going to reduce the norm. So you get into like these local minimum, and sometimes you can kind of find your way out by looking over the columns you've already chosen and choose to remove them. Okay. Okay. So if I now subtract here, well, let's just quickly go and say R4 is going to be R3 plus X2. And so what's going to happen now is I'm going to get 0, 2. Wait, no, I want it plus X2. So this would be, so this goes to 0. That goes to plus 1, 1, 0, 0. Right? So now if I add X2 back again, I'm going to do this. And now if I add, now if I do R5 equals R4 minus X6, I should get 0, 0. Okay, so this was kind of a roundabout. I made a mistake, but if you fix it, then I can recover everything here. Okay, so this, I didn't have enough observations for this to work, and we actually saw this. I think there are examples in the notes and also in the book which go through examples which actually do work. The one, I'm sure the one in the book is one which is different than this, and that one I definitely engineered so it works. Okay, so I may ask you to run through this an example that I think should work in your homework. You know, if it works, it should be pretty. It shouldn't be too hard to do. Okay, so I want to just say quickly, and maybe if you want, we can talk about this more on Monday if you're interested. There's an algorithm called least angle regression, which solves for lasso exactly. And basically, how to think about this algorithm is that you basically start with t being really small. So I think of the hard constraint version of this, where I have the constraints on t, and I start with the constraint being very small, and then as I progress the algorithm, I increase the value of t. Okay, and the key observation, the first key observation, when you do this, and I make t just barely larger than 0, it's going to mean that that alpha will have exactly one coordinate, right? The right solution for alpha is going to be all zeros except for one coordinate when t is slightly bigger than 0. And then what's going to happen is, as I increase t in a linear fashion, this is going to stay true for a while until I need a second coordinate to satisfy the right answer. So that means as I increase t, that's the L1 norm of alpha, which means alpha j, let's say that's the coordinate which is non-zero, it's increasing, it's exactly t. Right? So at the beginning, it's exactly t. It increases in a way that's linear. And that happens until some point when I need two coordinates. And then what happens is I know as I increase t, the values of alpha j and alpha j prime, which are the only two coordinates, are going to increase again at some linear rate. And I need to solve for that linear rate. And you can write down a bunch of linear equations, and you can actually solve for this. And in fact, I can solve for the point. It turns out to be I think a quadratic equation, which you can take the first derivative of. I can solve for the point where I start to need two coordinates instead of one. I can write down some equations, and I can solve for that. And I can keep doing this. And I keep solving for the point where I add one more coordinate. Okay? And I can do this one at a time as I'm increasing this value of t. And in between, for every value of t, there's a kind of a linear change in the correct coordinates. So if I trace these out, what's going to happen is the coordinates will start along here, and then at some point, they're going to move up like this. Right? So the coordinates will actually look like this linear sequence here. As I increase the value of t, I'm able to kind of get closer and closer to alpha. And they're going to be, I can describe it as a kind of a bunch of linear steps. Okay, so you can do this. The one tricky thing about it is the exact solution sometimes sets coordinates to be non-zero, and then they have to go back to 0 again. They become sparse again later on. So for small values of t, they're non-zero. For larger values of t, they're back to 0 again. And I think there's some worst case results that you may need an exponential number of steps. So there's some weird cases that, but you can actually write down the solution for every value of t. I can figure out the exact solution here following this formulation. Okay, and I don't think I need to go into any more detail. There probably is software out there. I wouldn't actually implement this. Okay, and then we'll talk about how to choose the correct value of S or T next week. So that's what we'll do on Monday.